So this lecture video is from Chapter 17, Additional Aspects of Aqueous Equilibrium, but it's about weak acid and strong base titrations, as well as strong acid and weak base titrations. So before watching this one, watch the strong acid, strong base video. That's the best place to start, because we're going to be using what we did in the strong acid, strong base, and then adding to it. Also, before we get too far in this, I want to make sure that you realize that the beautiful worksheet or handout that's called the Summary of Solving Acid-Base Calculations is your friend. And if you don't have this, go to Chapter 17's page in Canvas. So clicking on the chapter notes and practice worksheets and then going to Chapter 17, and it's called Summary of Solving Acid-Base Calculations. Either print it out or have an electronic copy for you to refer to. We're going to be looking at the weak acid and strong base and the weak base and strong acid categories at this point. Just a reminder, those are the steps that we're going to be following. So, nope. And bam. There. Okay, so we're gonna jump in. So this is another titration curve, very similar to the titration curve we saw in the strong acid, strong base, as well as hopefully similar looking to the titration curves that you made for your own data with the acid dissociation constant of a weak acid lab, because you did a titration between a weak acid, your unknown weak acid, and a strong base, sodium hydroxide. This is pretty much what your titration curve should look like. So we're going to talk through the calculations on how to calculate what the pH would be along any point in this, because you're not always going to have access to the lab to be able to do this. So we're going to do 4 example calculations, each of these pretty much each of these 4 spots. We're going to talk about how to calculate if you just have the initial acid, so like at 0 milliliters with your burette, how to calculate the pH once you've added some, how to calculate the pH when right at that equivalence point spot, and then again once you continue adding. So at the end of this, the only 2 spots that are different are really the initial acid. There's only 1 chemical there, so we're going to handle that one differently. And the equivalence point is just your least favorite one of these. But the second and the fourth ones, it doesn't super matter what's happening. We handle them the same way. I'm just going to do 4 calculations to get lots of practice. So again, the post-lab questions that go along with the acid dissociation constant and the base dissociation constant, I think it's number 2. There are 4 parts, part A, part B, part C, part D. They're practicing this. So these take some time and take a lot of practice, and so I'm really the worst because I'm forcing you to practice by making them part of required assignments. So, sorry. So for a titration of a weak acid and a strong base, at the equivalence point, the pH isn't always going to be the same thing. It's going to be different, but it's always going to be greater than 7. And that's actually on that beautiful handout. Down at the bottom, at equivalence point of titration, where it says weak acid and strong base, pH is greater than 7. So part of what we're going to be doing is solving for that. But we know for sure that it's always going to be greater than 7 if it is a weak acid and a strong base. And so when we do weak acid, strong base titrations, if we were using an indicator, we would use phenolphthalein. Because if you look at the titration curve, this is where the jump happens, right in there, right? Okay, so the orange colored bar it shows when methyl red, the indicator methyl red, when it changes color. And the pink purple colored bar is when phenolphthalein changes color. So if we look at this, the methyl red, it changes color, but it doesn't change color at the equivalence point. The equivalence point happens up here. And so phenolphthalein changes color at the equivalence point, which is why phenolphthalein is the indicator that we use for weak acid, strong base titrations. Methyl red would change color. It would. It just wouldn't change color at the right time. You would think you were at the equivalence point when you really weren't. So there's just a bigger version of the same picture. And just because weak acids are not all the same. Strong acids, I mean, they're 100% dissociate. They're all pretty much the same. We don't see big differences in their pH or the titration curves, but with weak acids, there's a range. There's depending on their Ka values. So the titration curves all look pretty much the same, but they kind of level out a little bit the weaker the acid gets. Okay, so first calculation is going to be before any of the base is added. So if you think about when you guys did your titration, it's when you had the 25 milliliters of the weak acid in the beaker, stir bar stirring, pH meter was in there, your burette was full of sodium hydroxide, but at the 0.00 point, like you hadn't opened up your burette yet. Let's see if we could calculate what the pH would be without being in the lab in that situation. So for this entire set of questions, I'm just using HA to represent the weak acid. So when you read these questions yourself, like when you're doing mastering chemistry, when you're working on the discussion, when you're doing post-lab questions, whatever, it could be benzoic acid or carbonic acid or I don't know, phenol, whatever the weak acid is, it doesn't matter. It's still in the same category. So I just went generic and I'm just calling it HA. So if we start out with 50.00 milliliters of a 0.0170 molarity solution of HA, the HA has a pKa value, so I've already taken the negative log of the Ka and gotten 6.37. We're supposed to find the pH. So when we approach these questions, or any questions in chapter 16 or 17, the first thing I want you to do is, no, I guess not green, is look at the chemical and identify it as what type of chemical it is. Is it a strong acid, a strong base, a weak acid, a weak base? So in this question, there's only one chemical, and that's HA. And HA stands for weak acid. Okay, so we read the question. I don't care about the numbers yet, but I notice that the only chemical I have is a weak acid. So I would refer back to that lovely handout, the summary of solving acid-base calculations, and look at the box that says weak acid only. And in that box, it gives us the equilibrium equation for HA, and underneath it says ice table, and then says calculate the pH using H3O plus from the ice table. This is just like the questions that we saw in chapter 16. This is just a weak acid only question. So I would start this by writing HA plus H2O equilibrium H3O plus A minus. Okay, now I'm going to write it little up here. We know that Ka is equal to products over reactants, so H3O plus A minus over HA. Okay, so we're trying to find the pH, so we care about H3O plus. So since this is at equilibrium, I'm going to do my ice table. So here's one I would normally ask. What units are allowed to be in the ice table? And there are only two answers that are correct, molarity and atmospheres. Well, in this question, we have a milliliters, we have a molarity, and we have a pKa. So the only one of these that's allowed to be in the ice table is the molarity. So for HA in the ice table, I'm going to change colors here. I'm going to write 0.0170 as the molarity right there. I'm going to cross out H2O because it's a liquid. We were not given any initial amounts for these two chemicals, so I'm going to go ahead and put zeros there. Now we're going to fill out the change row. This side's going to be minus, and this side's going to be plus, and I know that the product side is plus because we're starting at 0, and we're going to add it to whatever the change row is to get our equilibrium. It can't be negative, so whatever, if I'm starting with 0, I have to add a number to it, so it has to be plus. So this is a 1:1 to 1:1 mole ratio, so that's what I have there. If we look at the question, we were not given any equilibrium values, so I'm just going to take the initial row plus the change row to give me these. That's glorious, but I need to solve for this number. I need a number there so I can solve for pH. So at this situation, my ice table is complete. There's nothing more that I can add, but I still don't have my answer, so we're going to plug everything into this. Now, we have the H3O plus equilibrium is X, A minus is X, HA is 0.0170 minus X, and that's going to be equal to the Ka. Well, if we look back at the question, we weren't given the Ka, we were given the pKa. So just a quick reminder, pKa is just the negative log of the Ka value. So we're going to actually have to do this math. I'm going to take 6.37 and plug it in for Ka, or pKa, and I'm going to solve for Ka. So what's going to happen is when I rearrange this, this is what it's going to look like. 2 decimal places, oops, is going to get me 2 sig figs. I don't want to round quite yet, but I got 4.266 times 10 to the negative 7th is what I got. So 2 decimal places, 2 sig figs. So that's my Ka value. Okay, so what I'm going to do now is take that Ka number and my equilibrium, and I'm going to plop them in over here. So I'm going to say 4.266 times 10 to the negative 7th is equal to x times x, so I'm going to write x squared, over 0.0170 minus x. So we look at this, we have to solve for x, so we need to think, can I do the shortcut? So do you remember what the rule is on the shortcut? What does the equilibrium constant have to be? Well, it has to be times 10 to the negative 8 or smaller, times 10 to the negative 8, times 10 to the negative 9, negative 10, negative 11. This is negative 7. So what we're going to have to do is the quadratic formula. So I'm going to be super lazy, and I'm going to write the words quadratic. Yep, I can spell. Formula, and tell you I did the quadratic formula, and x equals 1.03 times 10 to the negative 4th. Okay. So I cross-multiplied, I distributed, I got everything on the same side. I did negative b plus or minus square root of b squared minus 4ac all over 2a. I did all that, and then x is what I got here. So I have x. I can go back and put that into my ice table. And I could plug it in right here, and right here, and right here. Well, to solve the question, all I super care about is that H3O plus is equal to x. So I ran out of space. So what I'm going to do is I'm going to go over to the next slide. I'm continuing the same problem. I'm just going over to more blank space. And I'm going to rewrite that x is equal to 1.03 times 10 to the negative 7th. Nope, negative 4th. Hold on. Yes, I just told myself good job. So we know that the equilibrium H3O plus number, I'm going to write EQ just so we remember that, is equal to x, which is equal to 1.03 times 10 to the negative 4th. The reason why I knew that the H3O plus equilibrium was equal to x, because my ice table at equilibrium H3O plus was x. So if I'm trying to solve for pH, don't I know that the pH equation is the negative log of H3O plus? So to solve for pH, I just need to take the negative log of 1.03 times 10 to the negative 4th. This has 2 sig figs, so my answer should have 2 decimal places. When I did this, I get 3.99. Now at the end of the question, this whole problem was about a weak acid. That's the only chemical that there was, a weak acid. So we need to look at our final pH, 3.99, and think, is this acidic, is this basic, or is this neutral? Since it's under 7, this is acidic, which makes sense if I have a weak acid. That's the only chemical I have is a weak acid. Once we start mixing chemicals together, acids and bases, it's kind of hard to predict what the pH is going to be at the end. But if you have just one chemical, the pH should reflect the type of chemical that it is. So it's a way to double check you didn't screw up your math. Or maybe. Okay, so we've got 3 more calculations to do. That was just our first one. Now we're going to do one where we actually started the titration. So this is just giving us the heads up of what we're going to do. You don't have to have all this. You don't have to know all of this. I'm just giving you the heads up of what's getting ready to happen. We will be using the Henderson-Hasselbalch equation. But again, you wouldn't necessarily know that up front, and that's fine. So let's look at the question. We're supposed to determine the pH when I have this much of this and its sodium hydroxide is added to this much of this of HA. So again, step number 1 is going to be, let's figure out the type of chemical. So sodium hydroxide, that's a strong base. HA, that's a weak acid. So we read the question and we have 2 chemicals, a strong base and a weak acid. To figure out what to do with those, we're going to grab our handout, the summary of solving acid-base calculations, and look for the box that says weak acid and strong base, which is at the top of the 3rd column. So we're just going to follow the directions there. It says number 1, write a balanced equation. So we're going to mix these 2 chemicals together and write the balanced equation. So NaOH, HA, arrow, and it's a metathesis or double replacement. So that means H and OH are going to be together, and Na and A are going to be together. So HOH makes water. And sodium and this A minus thing make that. Okay, I'm going to change colors here. Go back to purple. I want us to go ahead and let's write the type of chemical all 4 of these are. So NaOH is a strong base. HA is a weak acid. H2O is neutral, so I'm going to write X. NaA is not immediately apparent what it is. It's an ionic compound, so we need to look at this. So ionic compounds, that's when we look at the positive charge and the negative charge. So sodium is a positive charge. positive charges are acids, except for the list of exceptions, which are the things that are on the 8 strong bases. So sodium is one of those, so that's an exception. A minus, well, it's a negative charge. So negative charges are bases, except for that list of exceptions. A minus is not one of those exceptions. So this is a base. So this whole compound is a base. So we need to decide what kind of base, though. It's either strong base or weak base. Well, since it's not one of the 8 strong bases, this is a weak base. Okay. Anything that's neutral, we can ignore. This time, water is the only thing I get to ignore. Anything that's an acid or a base, we do have to calculate. Okay, so looking at our table, the weak acid and strong base on our handout, we wrote the balanced equation. Good job. Number 2, it says convert to moles of each chemical. So now it's time to look at the numbers. So we have 4 milliliters of a 0.1 molarity sodium hydroxide. I'm just going to write this down right now. 4 milliliters of a 0.1000 molarity. We have 50.00 milliliters of a 0.0170 molarity. And we have to solve for moles. Well, none of those numbers are in moles, so I am going to have to do the math here. So this is 0.000400 moles. And this is 0.000850 moles. Now, over here, I crossed out water, so I get to ignore it. But over here, the NaA, the weak base, we need to know moles of that as well. Well, we didn't have any, so it's 0 moles. It kind of works like an ice table, but it's not an ice table because this is not molarity, this is not an equilibrium, but we're just keeping track of stuff. Okay, so that was number 2, convert to moles of each chemical. Then it says, subtract the limiting reactant and add to the conjugate base product. All right, so the limiting reactant, we're looking at the moles that we started with, so just on the reactant side. We got to find the one that's the smallest, so 0.000400 or 0.000850, so 0.0004000 is the limiting reactant. So I'm going to subtract that from both sides, which is what we did with strong acid, strong base. And actually, if you're remembering that last video, this looks exactly the same so far in terms of math, other than the NaA not being crossed out. So I'm just going to go ahead and subtract. Oh, sorry. That's a 0. So my answer is 0.000450 moles. So that was the subtract the limiting reactant. We did that. And then it says add to conjugate base product. So we're going to add to the other side. So the reason why we're adding over here, well, these are the products. This is getting created. This is getting made. So we started with 0, but when the sodium hydroxide and the HA reacted, they're going to make water, which we don't care about, and NaA, so now we need to know how much there is. So we've now created, or we've figured out what we have left. So at the end of this, sodium hydroxide is gone. HA, we still have some of that, which is a weak acid, and NaA, we still have some of that, which is a weak base. So what we have left is a weak acid and a weak base, and we need to solve for the pH. So to figure out how to do this, we can go back and look at our chart and look for the weak acid, weak base section. And we're going to solve using that. So we're going to solve, because we have a weak acid and a weak base, we're going to use the Henderson-Hasselbalch equation. I'm going to be lazy and write WB for weak base and WA for weak acid. So we're trying to solve for this. So pH is what we're solving for. pKa was actually given in the question, 6.37. Plus the log of weak base. Now I know the brackets around WB stand for molarity, but if you remember this Henderson-Hasselbalch equation, since there's a numerator and a denominator, as long as the units are the same, it doesn't actually matter what units you put in there because they'll cancel out when we divide. So I'm going to leave them as moles. If that bothers you and you want them to be molarity, then you're going to take the moles down here at the bottom and you're going to divide them by 0.05400 liters. The volume would be the total volume, the 50 plus the 4. Okay, but I'm just going to leave it as moles. So I'm going to put weak base, whoa, hey buddy, on top, 0.000400 moles divided by 0.000450 moles. You see our moles are going to cancel. So when I do this math, I get an answer that is 6.32. So that was us solving for a weak acid, strong base titration. Okay, we did an example. So we've done it when we had 0 milliliters of strong base that we added, and now it was at 4 milliliters, whatever. Just we added some strong base and we did the calculation. Okay. That was in case we needed more space. So the half equivalence point, I've actually mentioned this. We used this idea in the lab. The half equivalence point is a special spot because at the half equivalence point, that means half of the strong base has reacted. So it's halfway to the equivalence point, and half of the strong acid has reacted. So we have a mixture of weak acid and weak base, which is the product, and they're equal to each other. So for the Henderson-Hasselbalch equation, what that does is it makes this ratio 1. The log of 1 is 0. So at the half equivalence point, pH equals pKa. This is how scientists figure out what the pKa, and then they calculate the Ka from that is for chemicals. So at the half equivalence point, the pH is always equal to pKa 100% of the time, okay? Because of the Henderson-Hasselbalch equation. Oh, look there, it shows all that. All right. So at the half equivalence point, we don't really have to do a whole lot of math. The pKa is equal to the pH. At the equivalence point, okay, so at the equivalence point, there's two different questions that I can ask, and we're going to do both of them. One of them is me asking you to predict how much you would have to add of the strong base to get to the equivalence point, like how many milliliters would you need to mix together before you got to the equivalence point. And then we can also solve for what the pH will be. The pH will be different for a strong base, weak acid titration at the equivalence point every time. It's just going to be greater than 7 every time. We know that with a strong base, weak acid, it's going to be greater than 7, but I don't know exactly what it is. So first, let's calculate the volume. Okay, so the question, calculate the volume of a 0.1000 molarity NaOH needed to reach the equivalence point with 50 milliliters of 0.0170 molarity HA. So again, something we should always do is figure out, oh, that was super wrong. That's a strong base, and this is a weak acid, okay? So those are important things. The other important thing about this question is it specifically mentions, yep, the equivalence point. We're at the equivalence point. The special thing about the equivalence point, oh, that was just the pKa, that's fine, is at the equivalence point, M1V1 tells us acid equals base. This is at the equivalence point only. It's the only time this works. It doesn't matter what the chemicals are. If it's a strong base and a weak acid, if it's a weak base and a strong acid, if it's a strong acid and a strong base, it doesn't matter. At the equivalence point, M1V1 equals M2V2. So we're going to use that to solve for how many milliliters of sodium hydroxide we'd have to add to get to the equivalence point. So using M1V1, M2V2, the molarity of the acid is 0.0170. The volume of the acid is 50.00 milliliters. The molarity of the base is 0.1000. The volume of the base, I don't know, so I would grab my calculator and do my math, and I get 8.50 milliliters. So at the equivalence point, we would have 8.50 milliliters of NaOH. That's when we would see that giant jump happen. Okay, so that's one question that I could ask. I asked the same question with strong acid, strong base, and we answered it the exact same way. Okay. The second question I could ask about the equivalence point is to calculate the pH. Okay. So what I didn't do was I didn't write down the volume. So at the equivalence point, we have 8.50 milliliters of NaOH. We solved that in the last question, so I'm just bringing that to this problem. We now know that information, so we're going to use it. So let's read the question. Classify our chemicals. NaOH is a strong base. HA is a weak acid. And we're calculating the pH. So now we look at our table, and it's a weak acid, strong base. So step 1 says to write the balanced equation. So NaOH plus HA, arrow, H2O, NaA, strong base, weak acid, neutral, weak base. I didn't go through this because we talked about this equation before, but I used the same thought process on this. So step number 2, It says to convert to moles of each chemical. So I'm going to write down the information I have. So I have 8.50 milliliters of a 0.1000 molarity sodium hydroxide. I have 50.00 milliliters of a 0.0170 molarity. I can ignore H2O, and I don't have any of the weak base. So it says step number 2 says convert to moles of each chemical. So that's what I'm going to do. I'm not showing my work to do this. You're going to be using milliliters, convert them to liters, and use the definition of molarity to convert to moles. Okay, so that was step number 2, convert to moles of each chemical. Step number 3, subtract the limiting reactant and add to the conjugate base product. So we're going to look at our moles and figure out our limiting reactant by which one is smallest. Well, which one's smaller, 0.000850 or 0.000850? Well, they're both the same, so they're both the limiting reactant. So I'm going to subtract 0.000850 from both. And then it also said to add to the other side because we're going to be making this sodium A stuff. Okay, so we did steps 1, 2, and 3. Step 4 says calculate the pH from the remaining chemicals, see whichever category is appropriate. So the remaining chemical, well, sodium hydroxide is gone, there's 0. HA is gone, there's 0. The only chemical left is the weak base, NaA. So this is the only chemical left. So all that we have left is weak base only. So if we go and look at our chart for weak base only, it shows us an ice table. Okay, so I'm going to change colors. We're going to have to go to an ice table now, which we can set that up and we will, but just a real quick question. What units are allowed to be in an ice table? There are only 2 correct answers, and that's molarity or atmospheres. And so molarity is our option here. We need our weak base, to be in molarity. Okay, so before I can go do my ice table, the molarity of weak base needs to be calculated. I have 0.000850 moles divided by the volume. So what do you think the volume should be that we use here? Our choices are 50.00 milliliters, 8.50 milliliters, or 58.50 milliliters. And the correct answer is the total, the 58.50 milliliters converted to liters. Because again, when we do a titration, we mix the chemicals together. So this would be divided by 0.05850 liters, which gets me 0.01453 molarity. So we now have a weak base. We have to do an ice table. So what I'm going to do is I'm going to go ahead and flip to the next slide to make sure I have enough space to set up my ice table. So since it's a weak base, my ice table is going to be like base. Oh, come back, buddy. Nope. Sorry. I hope this isn't giving anyone like motion sickness. Okay. AQ plus water. And if you look back on your table of the, okay, I will get better at this, I promise. Your summary of solving acid-base calculations, that's where this is coming from. This is also the equation we used in chapter 16. So I'm just writing down information. Okay, so we're going to do an ice table. We're going to ignore water because it's a liquid. And we need to put the molarity in for the weak base. So 0.01453 was the number that we solved for on the other slide. We put 0 in for the other chemicals. For my change row, minus x on the left and plus x on the right. I do not have any of the equilibrium values. So I'm just taking the initial row plus the change row equals the equilibrium row. So at this point, my ice table is as finished as I can get. I don't have numbers. I need numbers. I need to know the value of x, so that way it's equal to hydroxide ion, because then I can solve for pH. So this is the point where we need to plug stuff in. to the KB equation. But what we need to make sure we have is the value of KB. And in the question, the only thing we were given was the pKa. Now I'm going to cheat a little bit because we've also solved for the Ka, which was 4.266 times 10 to the negative 7th. So we solved for that back in the first calculation. We're on the third one right now. So what I can do is use this equation, plug in Ka right there, and solve for Kb. So that's what I'm going to do. I get 2.344 times 10 to the negative 8th. So I'm going to take my numbers and plop it into the Ka, or Kb equals x times x. There we go. X times x is x squared over 0.01453 minus x. But here's where I want to stop and think, can I use my shortcut? And my equilibrium constant is times 10 to the negative 8. So the answer is yes. So my shortcut means I'm just going to call this 0.01453. I'm going to get rid of the minus x. And the point of this shortcut is saying x is going to be super tiny, so small that if I take 0.01453 minus it, it's not going to change the number. The answer will still be 0.01453. So that's the point of this. So now I'm going to cross multiply and square root. So when I do that, when I cross multiply and square root, what I get for x is 1.9962 times 10 to the negative 5th. So that's equal to x. So x is that value. And the whole point of this is to get the pH. So what I need to know is hydroxide ion molarity. So I know that OH minus is equal to x, which we found was 1.9962 times 10 to the negative 5th. So what I'm going to do is plug the OH minus number into the POH. This has 2 sig figs. So my POH is going to have 2 decimal places. When I did this, I got 4.70. So then I'm going to say pH plus POH equals 14.000. So I'm going to plug POH right here, take 14 minus 4.70, and pH is 9.30. So that's my final answer for the pH. At the equivalence point, it's just long. We basically did 2 problems. So at the equivalence point of a strong base, weak acid, number 1, it's going to be a long problem. Number 2, the pH is always going to be greater than 7. So 9.30 fits that. So good job us. So by far, at the equivalence point for a weak acid, strong base is the longest one. Just imagine if we couldn't have done the shortcut and then we would have had to do the quadratic formula. Yeah, it could happen. It would be brutal, but it could happen and you could do it. But that's 3 of our 4 example calculations we're going to do for this. We have one more, same titration. I'm just picking a different spot along the titration, and we're going to do the math and see that it's okay. So after the equivalence point, again, you don't actually have to know where it is, but here's the question. We're going to start by identifying the chemicals, and then we'll go from there. I read the question. Sodium hydroxide is a strong base. HA is a weak acid. So I look at my chart. Strong base, weak acid. It says to write the balanced equation. Awesome. Change my color. I'm going to label everything. So strong base, weak acid, neutral, weak base. Again, this is the same balanced equation that I've done. So there's my label. Number 2 says convert to moles of each chemical. So sodium hydroxide, I have 13.00 milliliters of a 0.1000 molarity. HA is 50.00 milliliters of a 0.0170 molarity. None of those are in moles, so I'm going to convert them to moles. So this is 0.001300 moles. This one is 0.000850 moles. This is neutral, so I'm ignoring it. This was 0, so it's 0 moles. So number 3 says subtract the limiting reactant, add to conjugate base product. So we look at our two reactants. The limiting reactant is going to be the 0.000850 moles because it's the smaller number. And add it to the other side. So do my math, 0.000850 moles. This one's 0. This one is 0.000450 moles. Okay, so at the end of this, number 4, it says calculate the pH from the remaining chemicals, see whichever category is appropriate. So the chemicals remaining are the strong base and the weak base. So we're going to look at our table, and we find strong base and weak base. It's kind of near the bottom right corner. It says follow strong base instructions. So basically what I'm telling you is ignore the weak base. Okay. We know that the strong base is sodium hydroxide. We know that the molarity of sodium hydroxide is equal to hydroxide ion. And what I know is I have 0.000450 moles of it. So I'm going to, I guess, literally cross that out so we don't worry about it. But that's in moles. It needs to be in molarity. So I'm going to divide it by the volume, which will be the total volume, so 63 milliliters. When I do that math, I get 0.0071429. So the pOH is the negative log of OH minus, which is the negative log of 0.0071429. 3 sig figs, so I'm going to get 3 decimal places. I get 2.146 pH plus pOH equals 14. So pH is going to be equal to 14 minus 2.146, so 11.854 is my final pH. Okay. Whew, okay, we did all 4 calculations. That was if we needed extra space. So this was just a reminder again that our titration curves are going to look a little different for every weak acid that we use for this, which means our values are going to be different for every calculation because every acid is going to have its own Ka value plus its own molarity. So it's just going to be whatever it is. Okay. Now there's one more box on here that we haven't talked about yet, and that's weak base and strong acid. I can't imagine doing 4 more calculations at this moment. I know you don't want to listen to another video of that. So the good news is the weak base strong acid is almost identical to the weak acid strong base. It's just the labels above the chemicals are different. But it works the same way. So this is just a brief rundown of what happens. There's a box in there on our big chart for weak base and strong acid. You're just going to follow those steps. Those steps look almost exactly the same as the steps in the box above it for weak acid and strong base. So I'm not going to do more examples in the weak base lab. So the lab report for the base dissociation constant. Number 2 is letting you practice this. So I'm not going to go through it now. You're going to practice it, but you can refer to the 4 examples just before this as references. Okay. The titration curve for a weak base and a strong acid, it looks like the weak acid strong base, only it's like if we put a mirror in front of it, so it's the mirror image of it. It's just flip-flopped. And also, following that trend, at the equivalence point, the pH is going to be flip-flopped. Instead of being greater than 7, it's going to be less than 7. So we would use methyl red as our indicator if we were doing a titration like this, not phenolphthalein, because phenolphthalein does not change colors at the equivalence point. The other chemical, the other indicator is bromocresol green, which if you took Gen Chem 1 with us, you used it, it went from yellow to blue, it was green in the middle. That's another indicator that works for a weak base strong acid. Okay. If we had a polyprotic acid, H2 something, H3 something, its titration curve would just have more than one jump, more than one bump, one for each of the hydrogens. So you're not going to have to worry about that very much, other than if you see a graph that looks like this, all it means is it's a polyprotic acid. Okay. So that's the end of the acid-base portion of Chapter 17. We have one more video of Chapter 17 left, but it's like the other random things that go to equilibrium. So the acid-base stuff we've now completed.